So in this video we're going to extend our modeling examples a little bit by actually modeling the quartz porphyry zone, the red zone here in the middle, the granodiorite, the green zone there. We're going to explain a little bit more on the functional modeling as we go. So we go to our geology data here, so we have that available and we're going to use it. So similar to what we've done in earlier videos on creating the oxide layer, we're going to convert intervals, which we demonstrated before, and we're going to create another classification function. So here I'm going to select the quartz porphyry. We'll leave everything at the defaults again. It sets up the naming and everything, so just for now we'll just leave everything at the defaults. So again, we're going to run this one and go to the 3D view. It's just processing, and there you go, we got another representation of the quartz porphyry zone. So this is sort of like your implicit modeling, and it just takes an isotropic interpolation, as if you want to call it that. So it doesn't really look nice, but it tries to honor the data. So one of the things that's really powerful with these functions is that you can then say an anisotropy to it, saying, well, actually, I think that we need to have this anisotropy here. So I can draw this one, saying, okay, in that direction, so take this side view, and then I can change the strength along the major and median axis, and I can rerun this one. So now I'm going to have a same function. So this is the quartz porphyry function. It's just going to be updated. So as I said before, this is just a representation of it. So it sort of is a bit like the distance from the boundary between the quartz porphyry and everything else. So you see there's a bit of a jagged edge here, and that's just because of the resolution that we're using. So we can change that for that function to an intermediate, and then you see that it's already improving a little bit. We can change that even higher to make it even look better, but then everything slows down a bit. So now we have this function, and like I said before, because it's just a representation of the function in space, it's unbounded. It doesn't constrain to anything. It just says, okay, your zero level is here of that function, and everything inside is plus, everything outside is minus. So we sort of constrain it a little bit, but it gives you an idea of what shape this function will look like. I know some of you will probably not be happy with the shape here. I'll cover that in more detail in another video. What I'd like to do now is actually go back here, and we'll do the same for the granodiorite. Leave everything at the default just to see what it looks like. Changes this automatically to a new name, so we can rerun it, and then we can go to our functions here. So now we see two things. I'll turn this one off. One is dipping straight, or more or less downwards, and that's due to the anisotropy that we've set. But also it tries to honor the boundary here, which tends to cause some gaps. So first, let's solve the anisotropy. So I'm going to set that here. So just leave thing back to the default, and we run this again just to see what the shape will look like now. And there we go. It looks a lot better already. But as you can see, because it tries to honor these boundaries here, you might have gaps between the quartz porphyry and this granodiorite if you do modeling later. So to get rid of this, we go back to the processing tab, and in the step where we convert intervals to indicator points, we actually want to ignore the quartz porphyry because we've modeled that one already. This is considered the younger domain, so we don't need to constrain it by that one anymore. I actually want to have it a bit more unconstrained. So now you can see that it actually will go into the quartz porphyry zone here, and in a modeling step we'll show you how it will then automatically be constrained by the quartz porphyry. But again, this demonstrates the the difference between actual models and these functions, because here you see that the function is unconstrained, whereas our models will be constrained later on.